In this tutorial, I will explain how to implement an elevator control system using the chemical machine. The idea for this tutorial came from this blog post where the elevator control system was implemented using the ZIO library. The ZIO library is an effect system library. More or less, it implements asynchronous streaming with effects. And in this tutorial, it was shown how to implement an elevator control system with these specifications using this streaming library. And I thought it would be a good example if the same elevator system were implemented in the chemical machine to see how different it is when modeling a system using the chemical machine and using an effect library. So I'm going to take the same requirements and go to my chemical machine code. Analyzing these requirements, I found that actually there should be 3 more requirements added so that the system is complete. So here are the original requirements. Each elevator is situated on a certain floor and moves one floor by one floor at some fixed speed. Each elevator also has a list of next stops that it is planned to serve. Actually, I will probably remove this detail, so the next stop can be in any order, so it doesn't have to be in the same direction. Now, passengers are located on a certain floor, and they send a request to go to a certain other floor. That's an advanced elevator system. Usually, you don't have such requests. You just say you want to go up or down from your floor, but in this system, you can go from floor A to floor B, and the system tries to optimize that. The system will then look for a nearest elevator that is moving in the correct direction. So, for example, if you go from floor 2 to floor 5, and an elevator is at floor 1 going up, then that's a good elevator, but there might be an elevator on floor 3 going up or on floor 3 going down, and those are not suitable. And so the system will automatically choose a suitable elevator, and it will add floor A to the list of next stops on that elevator. And the system will also tell the passenger which elevator to wait for, since it knows the chosen elevator, and that's what the passenger can pick. Now, until the passenger is picked up, then the request remains active. Otherwise, the request must be deleted once an elevator that was chosen arrives at floor A. So the 3 additional requirements that I added were that if the elevator is out of stops to serve, then it remains idle at the floor where it was last, and this elevator can pick up new requests. So this elevator is not moving, but it's ready to start serving some new requests. Now, these requirements also don't say what happens if the system cannot find an elevator. Now, in this case, a request needs to wait, obviously, and that's a new requirement, that the request waits until an elevator is available. So in practice, an elevator must become idle before it can pick up a waiting request, because otherwise the request would have been picked up by some other elevator. And so the system doesn't just look for elevators that are moving in the correct direction. The system should also accept idle elevators. And that's the third additional requirement. So now, with all these requirements, let's simulate the system using the chemical machine. Now, the first step is to understand what data needs to be concurrently handled. All that data needs to be put on molecules. That's the basic design approach that the chemical machine has. Now, obviously, each elevator has its state, which needs to be concurrently handled. And so let's call this molecule elevator, LF. And actually, we have several elevators, so we need several of these molecules. And one approach would be to have different molecules for different elevators. So it will be not just one molecule, but LF1, LF2, etc. Another design choice is that these molecules should be static. In the chemical machine, a static molecule means that there's always one copy of this molecule at the reaction site, unless this molecule is currently being processed by a reaction, and then the reaction should also emit one copy of that molecule again. So those are static molecules, and there are two advantages that persuaded me to use static molecules for modeling elevators. And one advantage is that the state can be read very easily, and static molecules have an extra facility in the Chymyst library so that you can read their state. Since static molecules are similar to atomic variables, then it makes sense to read their state. There's always one value that you can read. And that's what we would need when we want to choose an elevator that satisfies some condition. We need to quickly look at all elevator states, and that's much easier if you use static molecules. A second advantage of static molecules is that if you make a mistake in a reaction and forget to emit a static molecule, then you will get an error very early, and that will help you avoid those errors. And so that's the second reason why I use static molecules for these. In fact, while implementing this example, I made this mistake of not emitting the static molecules back, and I was immediately given an error message. The downside is that we would have to statically define each elevator as a separate molecule. And so it would be difficult to add more elevators at a later time, or to remove elevators from operation. It is possible to do that, but it's just more difficult. But for this example, that would be sufficient. So just to be more clear about our types, the elevator number and the floor number are denoted by these types. They're integer, but I just want to be clear which integer I'm talking about. Elevator state is modeled as a current floor and a list of floors. Now these are the next destinations of an elevator, and this list could be empty, and then the elevator is considered to be idle. It doesn't have any plan for the next stops. Here are some functions that implement the business logic. So for example, one step is to move an elevator one floor towards its next stop. So if the elevator is idle and the state is unchanged, and if elevator is not idle, then it moves one floor. Well, actually, I move one floor, so this is going to be either 0, 1, or -1. The 0 would happen when next is equal to current, but that we will avoid in practice. We will never have that situation, because when the next floor is equal to next, then we will remove the next floor from the list right here. And so this comparison is practically always going to be either 1 or -1. So we add 1 or -1 to the current floor, depending on where we need to move. And that's the next floor. And then we print a diagnostic message just for our test and make the new state after one floor advance. So that implements this requirement that the elevator move floor by floor, deleting next stop from their state when reaching that floor. So we implemented that two requirements. Now, passenger request, let's have this data structure. From one floor to another floor and the passenger name. So now let's implement functions that do the decision of whether an elevator accepts a request or not. An idle elevator always accepts a request, and the next state becomes this list. So it first needs to go to the from floor, and then after that it will go to the to floor, from whatever floor it is now. And a non-idle elevator may or may not accept a request, depending on where it's going. So if it's idle, then we know how to do it. And if it's not idle, it has a next, then we make this logic. So if the floor from which we request is above the current floor, but the next stop is also up, then the floor can be inserted into the list of stops. Or if the current floor is below the current position of the elevator and the next destination is also below, then also we can insert. Otherwise, we don't accept the request. So we accept the request only when we are now between the current position of the elevator. So that the request comes from a floor that's between the current position of the elevator and the next stop, but not equal to the current position. So if the elevator is at the current floor, it's too late to request. It's already doors closing. Can't request anymore. No. So these functions are just manipulating the state. And finally, we need a function that chooses an elevator. And that's done by taking a sequence of all elevator states and the request. And then we filter all the elevators that can accept the request, which is using that function. And we sort by distance, which is a distance from the requested floor. So we take the smallest one, and then we take the first. If it doesn't exist, then this would be an empty option. So that's an empty option here. Otherwise, we will give you an option of non-empty option of the number corresponding to the elevator index, which is this elevator number. Should probably call it elevator index. That's probably easier to understand. All right. And finally, here's a function that prints a message for the passenger to go to a certain elevator. And also for diagnostic purposes, it tells us where the elevator currently is. So these are just business logic functions that operate on states. And we're going to implement these requirements that have to do with synchronizing the state of the elevators and the passenger requests. So in the chemical machine, all we do is we model the data and the reactions between the data molecules. So for each elevator, we already have a molecule. Now, sending a request means that we need a molecule that carries the request data. So let's implement that. So first we have, let's say we have 3 elevators, and we have 3 molecules carrying the elevator state. These are going to be static molecules, so let's just define reactions that emit them as a static reaction. So this is the syntax for static reactions. Now, in order to simulate the movement of elevators, we need some kind of time ticks. And let's just do that. When an elevator gets a time tick, then we step the elevator and we emit another time tick after a delay. So these are reactions that emit a molecule after a delay. It just makes a sleep and then emits the molecule. So this is just a quick and dirty way of scheduling at a given interval. In the blog post that I showed first, the ZIO library was used to schedule things. So the scheduling there was fixed for all elevators, and it was done by the library. Now, here it's very easy to do by hand in the chemical machine. We don't need a special library function for scheduling, and we are free to schedule different intervals because all of these are going to be completely concurrent and running in parallel. So after these 3 reactions, every elevator will automatically update after a certain interval, and here we just, for testing purposes, we give unequal intervals so that the 3 elevators don't have the same speed. So request must be a molecule. Now, the delayed is a molecule that models a request that was not accepted immediately. So that is a situation that I had to add to the requirements. When there is no elevator that can immediately accept a request, then the request becomes delayed. And in practice, you have to wait until some elevator becomes idle. And then the delayed request can be accepted. So let's model that by the molecule delayed. So that would be a molecule that carries the same request data, but it shows that the request has been delayed. A passenger will not receive a notification about a delayed request until some elevator accepts it. So that's what will happen. Now, we need obviously a signal for an elevator to accept a request. Now, the elevator could accept it, but it could be already too late, depending on runtime conditions, because an elevator could have been in a position to accept a request when we were making that decision, but an elevator is proceeding while we are making the decision. So by the time we send an accept signal, it could have been too late. And in that case, we have to retry. So therefore, we need a signal that we'll send to an elevator, and the elevator will have to respond. So let's model these signals by the accept molecules. And the notification for passenger we could also model as a molecule, but right now it's not going to be very helpful, and let me just print it to standard output for simplicity. So now this is a reaction that models sending a request. So the request molecule is emitted, then we gather the states of all elevators using the volatile value method, which is available for static molecules. So the states now are the sequence of states of all elevators, and we use the choose function, which is defined before, to choose the best elevator if it exists. If it exists, then this is the best elevator. We send it an accept signal, so we find which accept molecule needs to be sent, and we emit it. If there's no elevator available, the request becomes delayed, so we emit the delayed molecule. The request molecule is consumed. Now, for testing purposes, we need to keep track of how many requests are still unfulfilled, otherwise our test will never finish. So that is done using the remain molecule. And here is the function that we will use to decide acceptance. Now, for example, this is a reaction for an elevator 1 receiving an accept request. It's changing its state according to the decision to decide whether to accept or not. Now, this decision is the same for all elevators, so I refactored it into a function. And the function takes this decision, which is already implemented as a pure function here, and if it can accept the request and a new state is given, then it prints the message to the passenger. It updates the remaining requests, since one request has been accepted, and it gives a new state. And if the request cannot be accepted, which means that the elevator already moved past the requested floor and cannot be persuaded to come back, obviously, then the same number of requests remain, and we actually re-emit the request with the same data, because maybe a different elevator can serve it, and the same reaction that we had here would run again, and the elevator state is unchanged, because this elevator cannot accept the request, so it's not going to change its state. And we define 3 reactions for 3 elevators to do this. And also note, the remain molecule is consumed here, and it's emitted back inside that function. So I'm just refactoring code so that it's less repetition. Now, certainly at this time I noticed that I'm repeating code a lot. I have 3 elevators, and each time I say which elevator does what, I do it 3 times. So that's just going to be for the first draft of this implementation. And once I understand what I want to do, I will refactor this so that there's no repetition. So what remains is to serve the delayed requests. If there's a delayed request, then an idle elevator should serve it. Now, idle elevators are those that have elevator states with empty list of stops. So I'm using pattern matching here in this reaction to start that reaction only when the elevator state has an empty array of stops. So then what happens is that I accept, this is obviously always going to accept, so I re-emit the elevator molecule and change its state to that which was found after accepting the request from an idle elevator. So that's the function idle accept. Then I print the message for passenger, and I decrement the number of remaining requests. So I do it 3 times. This is where I forgot to emit the elevator molecule, and that's a static molecule, so it must be emitted on the right-hand side, and I was given an error message. So that's basically all we need to do. So we have modeled one by one all the requirements. Each requirement was translated more or less literally into a reaction, such as this one. If an elevator is asked to accept a request, then it decides it, or if there's a delayed request and an elevator is idle, then the elevator picks up the request, and so on. So every requirement is translated into a reaction more or less literally. So I don't think very much about what needs to be done. I just translate the requirements into code. The last step is to finish the test. Now, I have finished implementing the entire logic, but if I run this system, it will never finish. The elevators will keep moving or being idle. I will never finish the test. So how do I finish the test? I'm going to emit 100 requests at random times, and I'm going to count how many requests remain using this remain molecule. And notice every time I accepted a request, the remain molecule was updated and its value was decremented. So eventually, I'm going to have a remain molecule with 0 as a value. At that time, I'm going to define a reaction that will start, and it will only start when all elevators are idle, and when somebody emits this molecule until finished, which is a blocking molecule that will wait until this reaction starts and sends it a reply. So then this reaction is very simple. It just emits the elevator molecules unchanged with their states, but sends the reply. And this reaction will only run when there are no more requests pending and when all elevators are idle. So having defined all these reactions, I need to activate them in a reaction site. So for simplicity, I do that in one big reaction site. Although with more careful analysis, I could split this into multiple reaction sites, depending on molecules that don't conflict, but just for this test, it doesn't matter. Now I need to emit the initial molecules. So I emit the 3 tick molecules. I emit the remain molecule with 100 on it. I emit the 100 request molecules, and I introduce random waiting so that each passenger just randomly at a random floor wants to go to another random floor, and I wait until all of that is finished. So that can be run, and I can have a diagnostic output that will tell me where the requests are going, where the passengers are requesting things, and so on. So let's see how it runs. So this is how it runs. It tells us when elevators become idle or accept requests are sent and passengers are requested to go to one or another elevator. So now you see things are slowing down a bit because passengers are basically waiting for idle elevators. We just have 3 elevators and we have 100 passengers. Okay, we're all done. You see at the end, the last passenger was asked to proceed to elevator 3, which became idle just previously. So then eventually they're all idle and we're finished. So that's how this all works. So now I will refactor all of this so that instead of a hard-coded number of elevators, we have an arbitrary parameter, which I call range, which is what is the range of elevators that we have. And in order to refactor this, I'm going to use the fact that reactions are values in the chemical machine and molecule emitters are values. And so every time I had, for example, this kind of code, I'm just going to have a sequence of 3 molecule emitters. And every time I have this kind of code, I'm going to have a sequence of reactions, which I'm going to generate using molecule emitters as values. So here's how it looks. The beginning of this is here. So elevators, these are molecule emitters. For each of the molecule emitters, I declare static reaction. Ticks are molecule emitters. For each tick and elevator, I zip them, and then for each of these, I have a reaction, which takes this elevator, this tick, and advances the state. So I just copied the code and replaced all repetitions with this kind of code. I have 3 accept signals. I have a single reaction, which is the request. I have a sequence of these reactions that make each elevator accept or reject a request. It's more or less mechanically replaced. So up to this point, I refactored the code so that I have no repetition. And then I hit a snag, because what happens in the last reaction in the repetitive code is that I have a reaction which goes like this. It consumes all the molecules for each elevator at once. Now, it's impossible to define a reaction that consumes an unknown number of molecules at once. The number of molecules it consumes must be statically specified. This is a limitation of a chemical machine. So I cannot just say, have a reaction where the input molecules are an array of unknown how many input molecules. So that doesn't work. I cannot refactor this. So I need to replace this single reaction with a reaction that would run with each idle elevator separately, and then accumulate all of those idle elevators so that I can count them. Since the number of elevators is a runtime parameter, I must count that at runtime. That's how many elevators remain idle. So here's how I do that. I have the count of idle elevators, which is going to be initially 0, and it should reach the final value range. Then I have molecules that will check for each elevator whether it is idle, and if so, it will increment the idle elevators. The reaction that does this looks like that. I consume the idle elevators counter, I consume the check idle, and I consume the elevator in the state that is idle. And then I re-emit the elevator, and I re-emit the idle elevators counter. Notice I do not re-emit the check idle. So this reaction will only run once if I emit check idles for each elevator. And that's exactly what I need. I need each of these reactions to only run once at the very end, after there are no requests remaining, and after each elevator becomes idle. So then what I just said is translated into a reaction by saying that if there are no requests remaining, I start counting idle elevators, and I emit the check idles for each elevator. And finally, the blocking molecule that's going to be emitted at the end is going to react not with remain 0 as it did before. The remain 0 is long gone, but it's going to react with the idle elevators that must have this range value. So notice I'm using Scala syntax for a pattern match against a fixed value. I'm free to do so because the chemical machine uses partial functions to define reactions, and I'm free to use all features of Scala in the patterns in the left-hand side of the reaction. That concludes the code. So now I assemble all the reactions. I define a reaction site. It's a slightly different syntax because now I have sequences of reactions that I have to assemble into one big sequence. So if you look at the type of this value, it's a sequence of reactions. And I need this syntax then to put a sequence of arguments into a multi-argument function. And I do the same thing. I emit the ticks, I emit the requests at random times, and I wait until finished. Exactly the same code. Now I'm going to have 5 elevators instead of 3. Well, I could have 10. And let me run this test. So now it's a runtime parameter, how many elevators I have, and it's not hard-coded anymore. So let's see how it runs. So all these elevators, it should be much faster. Yeah, it's going quite fast. And now we're done. So indeed, all the elevators became idle, all passengers were served, and the test is finished. So this concludes my implementation of the elevator problem. Certainly it's a toy example. There might be other important features to be added in a production system. And this tutorial illustrates a difference between modeling a concurrent system using the chemical machine and modeling it using, say, an effect library or streaming library, as it was done by other people. Here are some links for alternative implementations of the elevator control system. This is the code that I referred to first, and there are also several implementations using akka and an implementation using streams. Now certainly the implementation using streams is going to be somewhat similar to this one, and the implementations using akka are going to be somewhat similar to the chemical machine, because the chemical machine is very closely connected to the actor model, and it's not very closely connected to streaming systems or effect systems. So what are the similarities and what are the differences? Well, one important difference between a streaming system or an asynchronous effect system and a message-based concurrency system is that you need to define all the streams statically, and they go more or less sequentially through their data. So any kind of streaming problem, streaming system, could be run on a single thread using, say, a JavaScript implementation where there's only one thread for everything, or just for whatever reason, you can run a streaming system on a single thread and it will still run and produce the correct result, maybe more slowly, but it will produce the correct result. So a streaming system cannot truly simulate parallelism because it is required to produce the correct result when you run it on a single thread implementation. Whereas message passing concurrency, such as actor model or the chemical machine, both of them are message passing systems, they do not have this limitation. So they actually implement full unrestricted concurrency and parallelism. Also, notice that this implementation doesn't look very functional in the sense that we are dealing with specific events and specific data being created or destroyed implicitly. In our code, there isn't any mutation. There aren't any vars in the code. And they're just pure functions, and we don't seem to mutate anything. But actually, if you look at this, this is a declaration of reaction side with reactions. Now, this declaration could have been seen as an effect, because after this declaration, things start running potentially, and not before. So this is an effect. This is an effect. Also, look at the code of certain reactions. It's this kind of code. It looks effectful, so it is not purely functional because we are emitting molecules, and emitting each molecule is an effect. It's not a value. Molecules are not values. Emitting a molecule is not a value, it's an effect. But other than these effects, there aren't any more effects. Well, it is true that we printed things, but you could think that this printing is just a stand-in for some other molecule or something else. This is not important. What is important is that the code is almost purely functional except for emitting molecules. That is an effect. Very similarly to the actor system, where sending messages to actors or creating new actors are effects. They're not themselves modeled as values or functions. Whereas in a streaming system or in an effect library such as ZIO, everything is modeled as a pure value and then run at the very end. So that's a significant difference. However, I just showed how we translated each requirement more or less straightforwardly and literally into a reaction. So for example, an elevator that's requested to pick up a passenger will have to decide and so on. So that's modeled as a reaction. We have a molecule for an elevator. Let's look at this reaction, for example. The passenger sends a request, so that molecule is emitted, then something is computed, and then an accept request was sent to a specific elevator, and then this elevator receives that request, performs a specific computation, and changes its state by emitting a new elevator molecule with a new state, and possibly emitting other molecules. So this is the typical way that the chemical machine models systems. It takes specifications in form of behaviors. It translates the behaviors into a language of data, which data models each part of the system and how this data needs to be processed and new data generated. Each piece of concurrent data is modeled by a molecule. We have created a large number of custom molecules here for each part of data that needs to be concurrently handled. And then each requirement of business logic in terms of what needs to be done when is modeled directly using these molecules. So when the molecule is available, do this. When an elevator is available and the request comes, do that. So these requirements are translated directly into the language of reactions. And I showed also how you can refactor reactions to make their bodies simpler, and you can put code into functions. Functions can also emit new molecules. They can do whatever you want, more or less. And that's a very flexible way of modeling various systems. This concludes the tutorial.